Hi, I'm Adam. Welcome back to Godot Game Lab. In this video, we'll take a look at the Finite State Machine component. Now a quick disclaimer before we start and jump into this video. I won't go into too much detail about how finite state machines work in general. If you want to learn about that more in detail, there are a lot of great videos and resources out there. Even my deck builder course dives deeper into how state machines work in general and how we can apply them in game development. That said, let's see how we can take the idea of a finite state machine and turn it into a component in this component-based thinking. Now, designing components can be as easy as asking three important questions. What is the one thing that this component does? What data the component needs to do its thing? And finally, how does it communicate with the rest of the game systems? Let's tackle those questions one by one. So what is the one thing that a finite state machine does? Well, the main use case for a finite state machine in game development at least is to manage actor behavior by isolating logic into different states. And the state machine itself can transition or switch between those different states based on some triggering conditions or criteria. This component will be a very lightweight implementation of the state machine, but again, if you need a refresher on how state machines work or a more detailed breakdown, I'll link some resources downstairs, or you can also just go to the deck builder tutorials second video in which I detail the finite state machines more in general at the beginning or the intro section of that video. I'll link that downstairs too. Now moving on to the data side of things, what data the FSM component needs. There's one really important piece of data, which is what we call the actor. And usually when you see node-based implementations of the finite state machine in Godot, that means the finite state machine node's parent node. So for example, if you have an enemy character that you want to control with a finite state machine, then the state machine will be attached to that enemy scene, and the root node in that scene will be the actor. We just say that it's a node because we want the component to be as reusable as possible, meaning that we can use it for UI elements, 3D nodes, and 2D nodes as well. And there are a million ways to go about this in Godot. The way I do it is that this implementation will require zero setup, and we just automatically assume that the parent node of the finite state machine will be the actor. But of course, if that doesn't suit your needs for whatever reason, you can just always turn it into an export variable, right? Now, how does a finite state machine communicate with the outside world? For the most part, it's very self-contained because you want to manage all the behavioral changes and the transitions between the different states, right? But at the same time, I think it makes sense to delegate some of that orchestration logic and the transitions to the actor itself. So my preferred way involves two main ways of communication. One is providing a public method called change state inside the finite state machine. And that method does what it says on the tin. It changes the finite state machine or transitions the finite state machine to a new state. But the catch here is that the new state will also be returned from the method. So if we orchestrate anything on the actor level, then we can have access to all the new states when we transition between them. Another way of communication is providing a state changed signal, which will be emitted every time when the finite state machine successfully changes to a new state. Now, this isn't that useful in my opinion because, as I said, state machines are very self-contained or contained within the actor that they act upon, but still providing a signal like that works really well with Godot's philosophy. And one really useful use case for this actually is for debugging purposes. For example, when you want to display the current state of that actor with a label node, you can just connect to that signal, and whenever the state changes, you can update the label as well. You don't have to query this in every frame, right? Now, after answering those three questions, let's move on to the implementation part next. And we have to split implementation into two different scripts as well, because a finite state machine is not just one script, but we also need a sort of base implementation of the states themselves, right? Now, in this case, we'll start with the state, and you can see that it extends not from the node or the resource class, but from RefCounted. Again, I don't want to go into too much detail how RefCounted works. There are a lot of great videos and explanations out there. I'll link everything downstairs if you are new to RefCounted objects. The TLDR is that they are memory objects that are automatically deleted if there are no references to them outside of that object. And the reason why I picked this for my implementation is because I just don't really like having a separate node for each of the states. There are a lot of implementations, and I also did that in the past, where the finite state machine was a node, but all the states that the state machine can be in were also nodes. And it's really fine, especially for small games, but you need to be aware that nodes come with a resource overhead, right? Because they need to be part of the whole Godot scene tree lifecycle, like the ready, the process, the physics process, and so on. So it's not a big deal when you make a small game, but when your game grows in complexity, it might be a resource overhead. And I think that states in these state machines are almost always these self-contained, very scripted and algorithmic pieces of logic, and to me it just makes sense that we just create them in memory, and when we exit the state it automatically cleans itself up from the memory, right? Nodes always sit there when the game is running. So that's why we use RefCounted here. And all the states will have access to their actors, which is a member variable, and again we can just only say that it's a node here to make sure that the component can be used in 3D, 2D and UI contexts as well. So to do that we just say it's a node, and each specific finite state machine and their states can typecast that actor into whatever class they want to have there to provide auto completion. You'll see this very clearly when we take a look at the example code later. Now, what do all the states need to have? They need to have an enter method, which will be called once when the finite state machine successfully changes into that state. Sort of counter to that, they have an exit method, which is called once when the FSM changes into a new state, overriding this one. So it's kind of like a cleanup method, so to speak, if you want to delete or free up any references when you leave the state, this is the place to do it. And then they have a couple methods which correspond to the virtual methods that the node ecosystem has in Godot. One is called update, which will be called every frame. You can also call it process. This is something that's really up to you. I wanted to show both versions in the demo, but you can tweak these method names however you prefer them. So for process and physics process, I deliberately used the different names. I used update and physics update. Both of these will be called with a delta value, and they will be called from the finite state machine every frame or every physics state. The reason why I didn't use process and physics process here without the underscore is because a lot of people mess this up in my previous tutorials, putting the leading underscore or forgetting when calling the method that they shouldn't use the leading underscore, right? So you can use whatever naming makes sense to you. I just kind of wanted to show that everything works here as long as it makes sense to you. But finally, for the unhandled input, I've used the same name that the Godot ecosystem has for nodes. It's underscore unhandled input by default, and here we leave out the underscore. Why? Well, I'll explain it in a second. Again, this method will be called whenever an unhandled input event occurs in the game. And this is something you usually want to handle within a state machine, right? Now for the FSM itself. We'll start by having a custom icon to make the component feel like more part of the Godot ecosystem by default. Then we have the custom class name, and we extend from the node class. Then we have that one signal defined that we use for communication, which is called state changed. And then we have two variables. One is the parent, which, as we said, acts as the actor for all the states. And I defined it as an onReady variable reference, meaning that whenever the node will be ready in the scene tree, this parent variable will have the reference to the parent node of the finite state machine by default. And we also have a member variable for storing the current state of the finite state machine. And this needs to be a state. It doesn't really matter what kind of state it is. It can be an idle state for an enemy or a jumping state for a player character. What matters is that it's a state. So it has an actor and it has all the enter, exit, update, physics update, and unhandled input methods. Now, how does the state machine work? For all those empty methods that we defined in the barebones state class, we need to kind of delegate that logic from the finite state machine itself because it is part of the node ecosystem, right? This is the only node that we'll have. So every frame, if we have a valid current state, then we can call the current state's update method and just pass in the delta. Same with the physics process, right? And you can see here why I was kind of torn between using the same naming, like physics process and process here. Because you are calling a public method from a different class, the Godot convention is that you shouldn't have an underscore here, right? Because if we would call it underscore physics process, then it would look like current state dot underscore physics process. And we don't want that because the leading underscore usually means that you shouldn't call this from the outside because it's a private method, right? So calling it physics process without the leading underscore can be confusing, especially for beginners or people who are not that familiar with coding, but everyone can mess it up. I do sometimes as well. So some people would say it's crazy that I call these update and physics update in the state class, but some people just prefer this because then it gets harder to confuse the two. So I don't know which one's better. Honestly, I just wanted to show both the pros and cons of using both. And for the unhandled input, I actually ended up using the same name, but without the leading underscore, right? So that's the way I leave it for the demo code, but for everyone, I suggest to pick one of the two, which you prefer, and then stick to that one, right? Because the mix and matching might not be the best, but for demonstrating purposes, this is the best I could come up with. Now, all that said, we just delegate the input events and we provide a way for all the states to manage logic that needs to execute every frame or every physics tick. But the most important method here is the change state method, and we have a couple of interesting things here. First of all, you can see that we have one parameter for this method, and it's called new state class, and its type is GDScript, which is interesting. So we expect a GDScript resource, and we return the new state from the method as well. Now, why have I used this new state class with GDScript type here? Well, because it enables us to do something really cool. All the states can just be GDScript files in the project. We don't have to create a new resource for them. We don't have to create an empty scene for them just with one script attached to them or anything. If all the states that we use inside our game have a custom class name attached to them, we can just say when we want to change into a new state in the finite state machine, we can just say change state and just use the custom class name that we have for the new state. So for example, you'll see it in a second in the demo. We can just say something like change state player run state. It's super cool. We don't have to create a new reference or anything. We just pass the custom class name as the parameter, and this method will automatically create a new state RefCounted object from it. I think it's a really elegant solution and I really like it. But let me know what you think in the comments. Now, how does that work? First of all, we need to start by checking if we have a current state that is valid. If the state machine is in some sort of a valid state, we need to exit that state first. And we also immediately set the current state variable to null. This is sort of a safeguard in a way, because if we, for whatever reason, cannot change to that new state class, we don't want the state to linger in a previous one, right? We can then go into a non-existent state and just say that the whole finite state machine fails, but we definitely don't want to be stuck in the old state for our reference, because as soon as we call exit, it means that we are no longer in that state. Let's say for that 0.00001 second, that ellipses between exiting the state and entering the new one, we can safely say that we're in a null state between those two. Of course, in reality, this happens really fast, but we just want to make sure that the finite state machine doesn't really stuck in an old state ever. Now that said, what do we do? Well, we have to move on to the next state after exiting the previous one, and we can just use the GDScript reference we have, for example, player jump state, and just create a new instance of it, which is in this case a RefCounted object, store it in a variable, and then we do a very important safety check here. We need to check if the new class we referenced is inheriting from the state class. If it's not, then we throw an error message and return early from the method returning null, because if it's not a derivative of that bare bones state class we just implemented, then we cannot transition to it. But if it is a valid state, what we do next is update the current state variable reference to that new state. Then the parent member variable is injected to the current state as its actor. This is how all the different states of the finite state machine will have access to the actor that they act upon. Then we call the current state's enter method. And finally, when we entered into the current state, we emit the state changed signal, notifying anyone who's interested in it. And when all that's done and dusted, we return the new current state. So anyone who uses the finite state machine, which in most cases is the actor itself, can do whatever they want to do with that current new state. I know this might be confusing, especially without looking at an example, because this is really general. But this is, I think, a good general implementation that can be used anywhere in your game. Again, 2D, 3D, UI, doesn't really matter. Let's take a look at it in action, and hopefully it will make a lot more sense. If you like my content, please consider checking out my Ko-fi page, where you can donate one time or become a member and get early access to all my content and videos. So I have the project open here. Let's start with the scene setup first, shall we? So you can see that we have some background, some tiles, and some UI to get it out of the way, which is just displaying a bunch of status messages on how to interact with the demo. What is more interesting is that we have an enemy and a character node here. So for the enemy, it's an animated sprite 2D, which has a scene unique name and a script attached to it. And it has two raycast 2D child nodes, a label displaying its current state, a timer, and a finite state machine. You can see that for the finite state machine, we don't really have to set up anything because the enemy itself handles all the bits needed for this to work. Now, here's how the enemy works, if you remember from the demo. We have these two raycasts for the two sides, left and right. And what this enemy does is it starts in an idle state, spends 2 seconds in that idle state. After that, it automatically transitions into its patrol state. And patrolling means that it starts moving forward towards its current direction. And if the raycast is colliding with one of the tiles, then we just flip its direction and it's animated sprite 2D, so it starts patrolling towards the other direction. Again, just bouncing back and forth between the two sides. The enemy does this for 6 seconds and then transitions back to the idle state, and this goes on forever. Pretty straightforward stuff. We have a timer node for it. And also the animated sprite 2D only has one animation, which is set to autoplay on load and set to loop. So it will look like this both when in the idle state and when actually flying or patrolling. So this is the setup we have for the enemy. Let's take a look at the code before moving into the character, right? Now the enemy has one export variable, which is the fly speed in pixels per second, and a bunch of already variable references to all the nodes that it has, right? All these ones. And also a member variable for the current direction. It will start patrolling towards the right by default. Now, how do we manage all the transitions between the different states? Again, here's a graph to kind of just show you the logic. One of the benefits of using finite state machines is that you can draw graphs like this, right? And it's really easy to visualize how the transitioning happens between the different states and what the character or the object needs to do in every state. One of the cons of using a finite state machine is that the more states added, the more convoluted and more complex this whole graph becomes. But for some simple use cases, it's a brilliant solution. So let's take a look at how this looks in action. So inside ready, we call a private method called idle, which we are yet to implement, and also connect to the finite state machine's state changed signal with a little callback script that we have here. And again, as I said, this is just for debugging purposes. So what we do when the state changes, we update the label node's text property to the custom class name that we added for this current state, so we can see on top of the enemy which state we are currently in. The more interesting one is the idle call, which basically says that when the game starts, we want to put this enemy into the idle state. Okay, so what does the idle state look like? Well, we do a couple of things. We set a timer to 2 seconds and start that timer, call the finite state machine's change state into enemy idle state. And this is what I said when discussing the implementation, that I think it looks really clean, that we don't have to use a resource or we don't have to instantiate a new enemy idle state here. We can just pass in the custom class name saying that this is the state that we want to transition into. And we don't even have to use enums, which is again a very common way of handling states for a finite state machine. We can actually handle the transition here as well, because when the timer times out, we can connect it to the patrol method, because when the 2 second elapses, we don't need anything else. We can just say that, okay, now we need to start patrolling. And we use the connect one-shot flag here to make sure that multiple transitions won't trigger multiple calls for the patrol method. We just connect this once and then the connection will automatically be disconnected after calling that method. Similarly, we do the same for patrolling, but we actually wait for 6 seconds before going back to idle to make this a longer state, so to speak. And that's really all that we need from the actor's side or the orchestrator's side. Again, you could also argue that we shouldn't really set the timers here, and we can move this to the states enter method instead, which is actually a fine take. You can do whatever makes more sense to you. It's fine to do it here as well, but we can say that, okay, this logic of handling the timer and knowing what time you want to be in this state for would be the responsibility of the state itself. Or one can say that I think that this is the responsibility of the enemy itself. I think it doesn't really matter that much, both are valid takes. What this solution means, however, is that actually our idle state is, that's about it. We don't really need to do anything because the animation is automatically played and we don't really want to change it because we only have one flying animation. It's looping and autoplay by default. In the idle state, we don't really have to do anything, right? If we wanted to, we can play some sounds or display a different icon over the head of the enemy. But in this case, for this demo, we don't really need to do anything. So it's a bit silly, but we do need the class name and we do need it to be a state because this class name is what we use here when we pass in which state we want to transition into. Now, the patrol state is a bit different because here we actually want to do something. So one of the things I was talking about in the implementation part is that the actor itself is just defined as a node to make sure that we can attach a finite state machine to all kinds of systems in the game. So what is really handy to do when you implement a specific finite state machine in the game is to provide a member variable like enemy in this case, which is of type enemy. And when we enter the patrol state itself, we can just typecast the actor to an enemy because we know that it will be an enemy in this case, right? So from that point, when we enter the patrol state, we have auto-completion when we write all the other code for the state. And in this case, we want to do something every physics tick. And what we do is pretty simple as well. We want to check if the enemy's left or right raycast is colliding, because if either of them is colliding, it means that we need to flip the enemy's direction vector on the horizontal axis and also set the animated sprite's flip H property to the opposite that it was before, right? If it was flipped, then we turn off flipping. If it was not flipped, then we flip it. And finally, after checking for the raycasts, either way, we want to update the enemy's position based on its current direction, the fly speed that we set, multiplied by the delta to make it frame rate independent. Pretty easy stuff, and it really separates the logic, and that's what I was talking about in the implementation part, is that this patrol state, if you open it up in the script editor, it kind of speaks for itself what it does. And if anything goes wrong with the patrolling itself, you know where to look. And it's a very simple and short script, so it's easy to debug. The enemy itself handles all the different transitions, which are really simple in this case because it's just a timer timing out. Again, if you want to, for the patrol, for example, these two lines of code could easily be moved inside the enter method here. Of course, you need to update it to become enemy.timer.waittime. And you can just argue that the state itself can handle how long it will remain there. And yeah, it's perfectly valid to do so. For this demo, I don't really think it matters that much, so I just leave it as it was before. And before moving on to the character, hopefully that makes sense. And let's see how it looks in action. You can see 2 seconds elapse, and then we go into the patrol state. The label is updated, the raycast collisions for 6 seconds work as intended, and it keeps flying back and forth. 6 seconds, then goes back to idle for 2 seconds and keeps on patrolling. Pretty awesome stuff, right? Now let's see a bit more complex example in the case of the character, which will be a very easy and very basic platforming character. This video is not really about making the best or the greatest platforming controller. There are a lot of great videos on that topic if you're interested in making the snappiest, best Celeste-like character controller. Here I just wanted something functional because platforming character controllers are a typical example where a finite state machine is really good, I think. If you take a look at the character itself, it's a character body 2D. We have a bunch of export variables, all related to platformer movement, not specifically the state machine logic itself. It's just movement speed, jump force, air control, and gravity. We have an animated sprite 2D. This time we have a bunch of different animations. The idle is just 1 frame. We have the jump, which is again 1 frame, and we have a running animation consisting of 2 frames, looping. And we also have a fall animation, which is again just 1 frame, right? We have a collision shape 2D to make sure that the player collides with all the different tiles. We have a label displaying the current state of the player, and again, we have a finite state machine without any export variables to set. Now, all the logic resides within the player script itself. Some things will look really similar to what we did with the enemy, but we also have 3 other states that we need to take care of and all the transitions between the different states. While discussing the code, I'll leave the graph again up to make sure that it's easier to visualize how the whole character works. Inside ready, we will start from the idle state again and again connect to the state machine's state changed signal. It's the same code that we have for the enemy, just to display the current state's name. We have the export variables that we were talking about, and also the onReady variable references to all the child nodes that the character has. Now, if we move to the idle state inside ready, what does that mean? It means that we need to call the finite state machine's change state into the player idle state. And that's a way of communication that we were talking about in designing the component part, right? I said that the change state method also returns that new state, which is super useful if you want the communication lines and the transitions to be orchestrated by signals that the states emit. In this case, we have the player idle state. We'll take a look at the code in a second. And the player idle state has 2 unique signals. One is when the jump button was pressed, and one is when one of the movement keys, left or right, were pressed. And since we return that state, we can also establish signal connections between them. And I think it's super clean because in a way, the transitions between the graphs are handled by the actor, which is very high level thing. But the logic itself, what the character does in an idle state, how it behaves, which is within the rectangles in the graph, is handled by the state itself, and it's self-contained. I think it's a really good solution, especially with finite state machines. I think there's 100 different ways to do it in Godot, and I've seen all kinds of solutions, and I've tried all kinds of solutions myself. Personally, this is the one I like best, so that's why I'm so excited about this. Now we can come back to all these different connections and all these methods in a second, but in order to make sense of them, let us just know what we need to do inside the different states first. So if we move to the idle state, we can define 2 signals because from the idle state there are 2 ways to transition out. One is to press the jump button and go to jump state, and one is to press the left or right movement keys and start running in that direction. Also, we need auto-completion, so again, we can use the trick where we define a member variable, and when we enter this state, we can just typecast it, right? And here we actually want to do a lot of things. When we enter the idle state, we want to grab the animated sprite 2D node and play the idle animation, and when we idle, for the sake of simplicity, I don't apply friction in this demo, which is what is kind of the usual thing to do in platforming games. I just instantly zero out the horizontal velocity of the character. We also have physics update, which is kind of superfluous here. I included it just to be safe, but I think the demo would work fine without actually having this in the code. So what we do each physics tick is having a safeguard first. If we don't have a valid player reference for whatever reason, we don't have to do anything. But if we do, I just called move and slide here. If for whatever reason we can get into the idle state with having any residual velocity, we can still call move and slide to apply it. Realistically, this doesn't really happen because when we enter, we immediately zero out the X velocity, and we can't really go idle mid-air, so we don't really want to do vertical velocity either. And this is just sort of a safeguard or future proofing more than anything else. If we wanted to add horizontal friction to the game later, then it will be easier to add it if we say that the character should move and slide every physics frame with its current velocity. Anyway, the most interesting part of the idle state is the unhandled input events. So when we have an unhandled input event, if it's a jump, then we can emit the jump press signal. Otherwise, we can grab the direction vector on the horizontal axis with input.getAxis and pass in the 2 input actions that we have. In my case, it's move left and move right. And if it's nowhere near 0, it means that we want to move in either direction, so we can just emit the move pressed signal. And I really like using signals to transition between the different states because I think it works really well with Godot's philosophy, right? The idle state don't really need to know about the existence of other states, because you could theoretically do something like player.fsm.change state enemy jump state. Or sorry, not enemy jump state, but player jump state. And this works as well. So one could argue that introducing all these signals and connecting them in the character's script at the very top level is just overhead, but I think it's good to make a clear distinction, a separation of concerns as well. Again, these things are kind of always tricky and you can argue for or against them, but to me at least it makes a lot of sense to define signals for the states and delegate the orchestration part and the transitioning between the different states to the actor itself. Let me know what you think in the comments or how you usually do state machines anyway. But that's it for the idle state. So now we know how we emit those two signals, and we understand that if we change to the idle state and store it inside a variable reference, when moving to idle, we can say that when the jump pressed or the move pressed signals are emitted, we can connect the corresponding methods. So we have one called jump and we have one called run. Again, we use one-shot connections. When the signal gets emitted, the connection automatically disconnects after one method call. Now, what do we do in the jump state? Again, we have two ways to transition out of the jump state, landing with and without movement. And by movement, I mean horizontal movement. So when we just stay in place and press the jump and press no other buttons, we jump up, we land, same position, right? In this case, we don't want to transition into running. That would be super weird. We want to transition into idle, right? But if we land while pressing one of the horizontal movement keys, we can immediately transition into running state, completely bypassing the idle state, because that would mean playing the idle animation and then transitioning into the run, which would cause flickering with the sprites, right? So for jumping itself, we use the same trick. We have a player variable here, typecast the actor, play the jump animation, and immediately set a y velocity with the player's jump force. This is a negative value, so the character will jump up. And inside physics update, we do a bunch of stuff. This is not my best code. Again, you could refactor it, you can call it spaghetti, but this is just a demo, not the component itself. So first, if we don't have a player character that is valid, we can return. Otherwise, we need to check for direction first, because most platforming games have air control, meaning that when you do a jump, you can still move the character mid-air, but usually it's not the same speed that you have on the ground, right? Because of some air resistance or whatever physics term we need to use here. So we do two things here. If we do have non-zero horizontal input direction, it means that we want to air control the character. So in this case, we set an x velocity, and using the direction and multiplying the movement speed, I just use the magic number here. In production or in a course, I wouldn't do this. This could be its own export variable called air control or something. But wait, don't I have a variable called air control? Oh, I do. So I just forgot to use it here. Let's quickly change this up to player.airControl. Got rid of the magic number. So what this means is that we take the player's movement speed and say that in this case, the default is 75%. You can only move 75% of what you usually could on the ground. And it might happen that as we air control, we need to flip the sprite to the other direction based on its direction. But what happens if we don't have any inputs given for air control? We could just zero out the x velocity like we did with the idle. But what I did here is I used move toward, which is kind of like smoothing it out a bit. It's like applying friction for the air control itself. We take the current player velocity, say that eventually we want to have 0x velocity, and we move towards that with this amount. To have a kind of a big friction, or quick or strong friction, I've used the player's move speed times 2. Again, you could do an air control friction export variable and just use it here or something like that. Right, so this is all related to horizontal movement midair. What's more important than this is the y movement, which is the jumping itself. So what we do is we take the player's y velocity and apply gravity times delta to it accumulatively. So adding to it every physics tick. The jump will still be performed because, again, when we enter the jumping state, we set a negative value for the jump force, and the positive value, the gravity will always apply each physics stick, right? And then when we have the x and the y velocity components handled, we can finally call character body 2d.move and slide. And then after moving, we can check for the signal emissions. So if the player is on floor, it means that we somehow landed. And since we already have established the direction vector for this frame, or for this physics frame, we can use that information whether we wanted to move horizontally this frame or not. If we have a non-zero input, it means that the landing with movement signal gets emitted, but if we had no input, just the basic landed signal will be emitted. Pretty straightforward stuff, right? So if we go back into the characters script, when we call jump, this is what happens, right? We call FSM.changeState with the player jump state, store that new state as a variable reference so we can make signal connections. For the basic landed signal, we need to connect it to the idle method that we already have, right? This will establish the transition from the jumping state to the idle on the graph. But if we landed with movement speed, we need to call the run method, which we are yet to look at. Now, before handling running, let's take a look at the run state itself. In this case, we actually have three signals, three transitions, which are slightly different. So stopped will be emitted when we no longer press any horizontal keys and the character needs to go back to idling. Jump pressed will be emitted when we jump while running to, well, execute a jump, but it can happen that we fall off a platform. And in this case, we kind of want to apply gravity as well, right? But if we just simply transition into jumping and handle it the same way, it would be super weird. Why? Well, because jumping starts with applying a jump force velocity. That means that if we fall down and just simply transition into a jump state, the character would execute an upwards jump on its own without us ever pressing the jump key. And that's super weird and unresponsive for the player, right? So we need to handle falling down a bit differently. But the running itself doesn't really care. It just tells the actor or the state machine or whoever wants to know about this that, okay, I just fell off a platform. Now, what do we need to do when we enter the state? Usual stuff, we grab a reference to the player from the actor and then play the run animation. Most of the movement happens inside the physics update. Again, if we don't have a player, we can just return. Then, like we usually do, we grab the direction vector on the horizontal axis. And if it's 0 or almost 0, I didn't really talk about this, is 0 approx. It's just a Boolean method for float that is 0 or close to 0. This is a good thing to do because floating point numbers are not very precise always. So if you just compare a floating point number to 0.0, you need to have that very specific configuration of 32 bits to say that they are equal. And it might happen that the stored value is something like this, right? And in this case, if you compare the two, it would be false because the two floating point numbers are not exactly the same in memory or converted to binary. So this is 0 approx is always welcome when you use floating point numbers and you want to test for equality, or in this case, if we have 0 or not. Anyway, if it's kind of 0 or very close to 0, then we can emit the stopped signal and return from this method because we don't have to run anything anymore, right? We don't have to move the player character if we stopped. Again, if you wanted to apply friction, it's a different story, but if you had a valid horizontal input direction vector, then we need to update the player's velocity's x component. We might need to update the flip h property of the animated sprite 2D, and we definitely need to call move and slide to move the player in that direction. Now, after moving, we can check if the player fell off a platform. So if the player is not on floor after moving with move and slide, it means that we can emit the fell signal safely. And finally, when running, we still need to override the unhandled input event method and say that if the jump action was pressed, we can emit the jump pressed signal. It doesn't really matter if the player was running, it has a direction vector, we just need to execute the jump anyway, right? So that's all for running, and let's see how we can orchestrate this to handle falling down. So you see when the run method gets called, we call change state and transition into the run state. We store that reference and make 3 connections to the 3 signals. When you stop inside the run state, we transition back to idle. When you press the jump button, we transition back to jump, which we already discussed. And finally, if you fell, we call another method called fall. And that's this cheeky little method right here. So what we do is actually the same as we jump, right? So all this will be executed. However, we can do something like this. When change state is called, if you remember the implementation, when this gets executed, we enter the current state. In this case, jumping means we go to the jump state and everything that we have inside the jump state's enter method will be executed. Meaning that by the time we arrive at the last line of code, the player's Y velocity will be set to the negative jump force. And we can just simply say that, okay, let's override that number with 0. And we can just fall down. It might not be the most elegant solution. An alternative would be to actually introduce a completely different state for falling. It could be called something like player fall state. And you can handle falling completely differently. But it's just a quick and easy solution here because when falling down, you actually want to do the same thing as jumping, right? Without the initial upwards boost. Because you still want to do air control and you still want to do applying the gravity, right? So this is a cool solution, and if you can write a two-liner like this, it shows that you really understand sort of the chain of events that happen when you change from one state to another and in what order these lines are executed. Okay, so enough of me speaking, let's take a look at this in action. So the player character starts from the idle state. If I press any of the horizontal keys, we go to the run state. If I let go, we go back to idle. If I press space, we go to jump. Yeah, we go back to idle if I don't move. If I move mid-air, we go to the run state immediately after I land. I can air control the character, and let's take a look at falling down. So if I fall down, we should not really do any sort of jumping without me pressing the space. Yep. We still transition into the jump state, if you saw that. But we don't really jump up, we just fall down as expected. Pretty cool, huh? I hope you found this useful, and I hope to contribute something new to the whole saturated finite state machine videos and resources that we have for Godot. I really enjoyed making this episode, so I hope you liked it too, and I'll see you in the next one. Bye bye.